How can a rail system built for conventional freight safely move cargo weighing over 1 million pounds without collapsing its infrastructure or losing stability? Every railroad on Earth is built around a hard limit, the maximum weight each axle can press down onto the rails. In North America, that ceiling sits at roughly 70,000 pounds per axle, a number set by decades of engineering experience and codified in federal regulations. This is the invisible boundary that keeps bridges from buckling, rails from bending, and the ground beneath from shifting under the weight of passing trains. Exceed it, and the risk is not theoretical. Steel can deform, concrete can crack, and a single overloaded wheel can spell disaster for an entire line. Yet industrial demand keeps rising. The world's largest transformers, generators, and reactor vessels now tip the scales at over 1 million pounds, more than 10 times the weight of a loaded freight car. Moving such a mass on rails designed for far lighter loads is not just a question of strength, but of survival. The challenge is simple to state and nearly impossible to solve. How do you move a 1 million-pound object across a network where every axle must stay below 70,000 pounds? The math is unforgiving. A standard 4-axle freight car, fully loaded, already hovers near the limit. Stack a 1 million-pound transformer on top, and the result would instantly overwhelm any bridge or stretch of track. This is where the real puzzle begins. To move the heaviest loads on Earth without breaking the rules, engineers had to invent a method that does not fight the limits, but works within them. The answer lies not in brute force, but in the art of distribution, spreading weight so precisely across dozens of wheels and axles that no single point ever exceeds the threshold. It is a balancing act on a continental scale, and the stakes could not be higher. The breakthrough that defines the Schnabel car lies in a simple equation: distribute the impossible. Instead of balancing a 1 million-pound transformer on a single flat car where 4 axles would each groan under more than 250,000 pounds, engineers take a different approach. They turn the cargo itself into a structural beam, clamped between 2 massive lifting arms that reach out from each end of the car. This is the essence of the Schnabel principle. The load becomes part of the vehicle, not just something it carries. The term Schnabel comes from the German word for beak, a nod to the way these articulated arms grasp the cargo. But the real magic happens in the numbers. Take a transformer and Schnabel car with a combined weight of 1.1 million pounds. Divide that across 36 axles, 18 at each end, and each axle bears just over 30,500 pounds. That is less than half the maximum allowed on North American rails. By comparison, a standard gondola car carrying 286,000 pounds over 4 axles pushes right up against the 71,500-pound limit per axle, leaving no room for error. This distribution is not just clever, it is essential. The force does not concentrate at a single point, but spreads out like a bridge spanning a river, minimizing stress on any one rail, tie, or bridge span. The result is a 1 million-pound load that glides across the country without overwhelming the infrastructure beneath it. What seems like brute strength is, in reality, a feat of balance and calculation, solving the unsolvable by turning the cargo into the very backbone of the train. Precision is the backbone of every Schnabel move. Each lifting arm is equipped with powerful hydraulic cylinders capable of raising a loaded transformer or reactor vessel up to 44 inches above the rails and shifting it laterally by as much as 40 inches. These numbers are not just for show. They are the difference between clearing a signal post by a single inch or scraping against it at a crawl. The entire lifting and shifting process runs on a closed loop of sensors and feedback. Load cells built into the clamps at each end constantly measure the force pressing down on every point. The real-time dashboard in the operator's cabin displays the weight on each arm, the pressure in each cylinder, and the exact position of the load, all tracked to within a 2% margin of error. Structural engineers point to this system as the key safeguard. If a bridge dips unexpectedly, or if the track twists on a tight curve, the hydraulics respond in seconds, redistributing force to keep the load centered and stable. The operator can fine-tune the height or shift the cargo sideways at a moment's notice, always watching for any deviation beyond the allowed tolerance. If the system detects an imbalance greater than 2%, alarms sound, and the movement halts until the load is brought back into line. This constant vigilance is what allows a million-pound transformer to float over aging bridges and through narrow tunnels without incident. Reliability is built into every link of the hardware. Dual hydraulic circuits provide redundancy in case of a failure, and each load pin clamp is backed up by a secondary lock. Maintenance crews inspect the cylinders and seals every 6,000 hours, and load cells are recalibrated annually to ensure accuracy. The result is a system that does not just move weight, it controls it with surgical precision, making what seems impossible routine. Speed is not just a matter of scheduling for a Schnabel move, it is a question of physics and safety. When a million-pound transformer rides the rails, every increase in speed multiplies the forces at play. Structural engineers point to a concept called the dynamic amplification factor. At 25 miles per hour, the live load on each axle can rise by about 15% compared to standing still. For a 1.2 million-pound cargo on a 30-axle Schnabel, each axle might see its effective load climb from 40,000 pounds at rest to 46,000 pounds in motion. That is still below the federal limit, but the margin narrows as speed increases. The center of gravity becomes the silent partner in this equation. If the load shifts even a few inches off center, especially in a curve or over a bridge, the balance changes instantly. On a 500-meter radius curve, the entire cargo can be hydraulically offset by several inches to counteract the centrifugal force. This keeps the weight distributed evenly and prevents the wheels on the outside rail from overloading. The hydraulic system does not just react to the track, it anticipates it, guided by route data and real-time feedback from load cells at every clamp point. Operating speeds for loaded Schnabel cars are capped between 15 and 25 miles per hour, not because the train cannot go faster, but because the infrastructure beneath it cannot absorb the extra stress. At these speeds, the dynamic factor stays within a safe band. It is 1.05 at 15 miles per hour and 1.15 at 25 miles per hour. If the speed goes beyond that, the risk of bridge deflection, rail deformation, or even wheel climb becomes unacceptably high. Every curve, every bridge, every mile is a calculation in motion, balancing mass, speed, and the invisible limits of the railway itself. Before a single wheel turns, the work begins far from the tracks. Every Schnabel move starts with a checklist that stretches over half a year or more. Route planners pore over bridge inventories, track class ratings, and clearance maps, searching for weak links along hundreds of miles. A single bridge with an uncertain rating can grind the process to a halt. Permits are filed with the Federal Railroad Administration, state transportation offices, and sometimes local municipalities, each demanding their own reviews and sign-offs. Laser surveys map every tunnel, platform, and signal post the car will pass, measuring clearances down to the inch. Insurance brokers step in next, arranging liability coverage that can top $500 million for a single haul, reflecting the risk if a million-pound load were to stress a bridge beyond its limits. Fewer than 100 Schnabel cars exist worldwide, and each one is booked months in advance, its schedule locked into a global dance of grid upgrades and industrial projects. The planner's job is to anticipate every problem before it happens, knowing that a single oversight could mean disaster for infrastructure, cargo, and crew alike. A million-pound generator approaches a bridge rated for only 1.2 million pounds, too close for comfort once dynamic forces come into play. The train slows to 5 miles per hour, every member of the 6-person crew at full attention. The hydraulic operator stands over the console, eyes locked on the digital readouts. Load cells report the generator's weight, 1.34 million pounds, distributed across 36 axles. But the bridge's margin is razor thin. As the lead wheels touch the span, the operator begins fine-tuning the hydraulic arms, shifting the load by fractions of an inch to keep each axle's force within the safe zone. The pressure in each cylinder is monitored to the pound. Any sudden dip or twist in the bridge, and the hydraulics must react instantly, lifting or shifting the cargo to keep the center of gravity balanced. The crossing takes nearly 3 minutes. When the last axle clears, the tension breaks. The bridge holds. Holes? The operator lets out a breath, knowing that precision, not brute force, carried the day. Today, the precision of Schnabel cars quietly safeguards entire regions' energy and industry. With fewer than 100 worldwide, each move is a rare feat of engineering, relying on discipline rather than brute force. Our modern infrastructure depends on these invisible giants, reminding us that behind every switch, logistics shape possibility. Share your thoughts below.